Let us begin a journey outward, a gentle float through scales of existence that stretch beyond the reaches of human comprehension. We begin here with Earth, our pale blue home, spinning silently through the void, not to understand it fully, but simply to feel its presence as our starting point, our anchor in the vastness we're about to explore. Look upward on a clear night, away from the glow of city lights. Those pinpricks of illumination scattered across the darkness, each one is a sun. Each one a sphere of nuclear fire blazing across distances so profound that the light touching your eye began its journey long before you were born. Some of that ancient light left its source when your great-grandparents were children. Some when humans were just learning to stand upright on an African savanna. But before we drift too far into that cosmic ocean, let us pause at something closer, something we can almost grasp. Jupiter, the giant of our solar system. A world 11 times wider than the Earth, 317 times more massive, a swirling storm of hydrogen and helium, spinning in the cold darkness beyond Mars. Jupiter is almost a star, almost, but not quite. It holds the same ingredients as our sun, those simplest of elements forged in the first moments after the universe began. But Jupiter gathered too little mass to ignite the fire that defines a star. And there are others like it, these almosts, these not quite stars, brown dwarfs we call them. Spheres of gas between 13 and 90 times Jupiter's mass, glowing faintly with the heat of slow fusion reactions. Neither planet nor star, but something in between. Failed stars, some say, though perhaps they are simply beings unto themselves, content to glow softly in the night, asking nothing of the universe but to exist. And so we move onward to stars. A star is born when gravity gathers enough gas, enough hydrogen primarily, into one place, compressing it, heating it, until the pressure and temperature at the core become so intense that nuclei begin to fuse. Hydrogen becomes helium, mass becomes energy. Einstein's famous equation, E equals mc squared, plays out in the heart of every star, converting the tiniest fraction of matter into floods of light that pour outward, pushing back against gravity's endless embrace. The smallest true stars are called red dwarfs, barely massive enough to sustain fusion. Roughly 100 times Jupiter's mass, they burn their fuel with such parsimony that they can shine for 10 trillion years. 10 trillion. a span of time so vast it makes the 13.8 billion years of age of our universe seem like a brief afternoon. Red dwarfs will outlive everything, outlive the age when new stars form, outlive the era when galaxies dance and merge, outlive perhaps even the age when life can exist on planets bathed in their patient, dim red light. Barnard's star is one of these, 6 light years away, practically a neighbor in cosmic terms, yet invisible to your naked eye, too faint, too small, too humble. But it will be here, glowing, long after our sun has exhausted its fuel and faded to a cold, dark ember. Our sun sits in the middle of this stellar spectrum, not small, not large, but somewhere beautifully, perfectly average. It contains 99.86% of all the mass in our solar system. Everything else, all the planets, all the asteroids, all the comets drifting through the outer darkness, amounts to barely a rounding error in the sun's gravitational dominion. The sun burns hotter and brighter than red dwarfs, which means it will live a shorter life, about 10 billion years total, and it's already halfway through. But this is still an incomprehensible time span. Mountains rise and erode, continents drift and collide, species emerge, flourish, and vanish into extinction, and through it all the sun shines on, steady and eternal from any human perspective. Yet even our sun is dwarfed by other stars in the galaxy. Consider Sirius, the brightest star in our night sky. Only twice the sun's mass, yet it burns so hot, nearly 10,000 degrees Celsius at its surface, that it shines 25 times brighter. But this intensity comes at a cost. Sirius will exhaust its hydrogen in only 2.5 billion years, a quarter of the sun's lifespan, burning brilliant and brief, like a match struck against the darkness. Go larger still. Stars with 10 times our sun's mass blaze with surface temperatures of 25,000 degrees. Beta Centauri holds 2 such stars, each radiating 20,000 times the power of our sun. They are magnificent. They are doomed. They will burn through their fuel in a mere 20 million years, a geological instant, barely enough time for complex life to evolve on any world that might orbit them. You might expect then that the most massive stars would be the largest. And for a time, this is true. R136A1, located in the Large Magellanic Cloud, a satellite galaxy dancing around our own, weighs in at 315 times the sun's mass. It blazes with the power of nearly 9 million suns. And yet, despite this tremendous mass and energy, it's barely 30 times larger than our sun in radius, How can this be? The answer lies in a delicate balance. When stars this massive form, they burn so intensely that their stellar winds, streams of particles blown off by radiation pressure, carry away material faster than gravity can hold it. R136A1 loses 321,000 billion tons of matter every single second. A hemorrhage of mass into space. Stars like this are rare, probably formed from the merger of several massive stars in dense stellar nurseries, and they live only a few million years before exploding as supernovae. To find the largest stars, we must look not at the most massive, but at the dying. When main sequence stars exhaust the hydrogen in their cores, something beautiful and terrible happens. The core contracts, grows hotter, begins fusing hydrogen in a shell around the helium center. This increased energy pushes the outer layers outward, and the star swells. It becomes a red giant, and later, if massive enough, a red supergiant or hypergiant. Our sun will do this one day, in about 5 billion years. It will swell to 200 times its current radius, its outer layers reaching beyond Earth's orbit, Mercury, Venus, possibly Earth itself, all will be consumed by the expanding photosphere of our dying star. But by then, if humanity still exists, we will have left long ago, carrying with us the memory of blue skies and green forests, of oceans and mountains, of this small world that gave birth to minds capable of contemplating the cosmos. But our sun's red giant phase, while dramatic on a human scale, is modest compared to the true giants of the universe, the hypergiants. Hypergiants are the final brief phases of the most massive stars. Their surfaces are so far from their cores that gravity can barely hold them together. They blow themselves apart with stellar winds, shedding mass in great streaming clouds that reflect starlight across light years of space. There is Pistol Star, a blue hypergiant 300 times the sun's radius, radiating such intense ultraviolet light that it ionizes gas clouds across dozens of light years. There are yellow hypergiants like Rho Cassiopeia, 500 times the sun's radius, visible to the naked eye despite being thousands of light years distant. Only 15 yellow hypergiants are known, suggesting they are merely brief transition stages, stars caught in the act of transforming between different phases of hypergiant existence. And then there are the red hypergiants, the largest stars known, perhaps the largest stars possible. Measurements of these cosmic titans remain uncertain, their exact sizes debated among astronomers as new observations refine our understanding. Recent studies suggest stars like WOH G64 and Westerlund 126 may be among the largest, while UY Scuti, located about 9,500 light-years away in the constellation Scutum, has long been measured at roughly 1,700 times the Sun's radius. Try to imagine this. Try to truly grasp it. If UY Scuti replaced our Sun, its surface would extend beyond Jupiter's orbit. The star is so large that light, traveling at 300,000 kilometers per second, would take nearly 9 hours to complete one circuit around its circumference. A passenger jet would need 500 years for the same journey. These stars are not solid spheres like planets. They are tenuous, their outer layers barely denser than the vacuum of space, held in place by gravity that grows weaker with distance from the core. They are dying, shedding their outer layers back into space, enriching the interstellar medium with heavy elements forged in their cores: carbon, oxygen, nitrogen, silicon, iron, all the elements necessary for planets, for life, for consciousness itself. One day, perhaps in a few 100,000 years, perhaps tomorrow by cosmic standards, these hypergiants will explode as supernovae. In a matter of hours, they will release more energy than they radiated during their entire lifetimes. For a brief moment, a single star will outshine its entire galaxy. The explosion will send a shockwave through space, compressing nearby gas clouds, perhaps triggering the formation of new stars. And those new stars will be born from the ashes of the old, the hydrogen and helium from the Big Bang, supplemented now with heavier elements forged in stellar cores and supernova explosions. Some of those stars will be red dwarfs, patient and long-lived. Some will be stars like our Sun, medium-sized and steady. Some will be giants and hypergiants themselves, racing through their life cycles in cosmic instants, returning their enriched matter to space once more. This is the cycle: birth and death, contraction and expansion. Stars form from gas clouds. They live, they die, and in dying, they seed new generations. The carbon in your bones, the iron in your blood, the oxygen in every breath you take, all of it was forged in the cores of stars that died before our Sun was born. You are made of star stuff, as Carl Sagan so beautifully said. Not metaphorically, literally. The atoms in your body have passed through perhaps dozens of stellar generations, each one adding its signature to the cosmic recipe. And this brings us back to scale, to perspective. The smallest measurable distance in physics is the Planck length, 10 to the minus 35 meters. It is so small that if you expanded a proton to the size of the solar system, the Planck length would grow only to the size of a cell or virus. At this scale, the fabric of space-time becomes uncertain. Quantum fluctuations dominate, and our current theories break down. From that unimaginably tiny scale to the orbit of Neptune, from quantum foam to planetary orbits, is the same ratio as from a human to the largest stars we've discussed. We sit in the middle, more or less, too large to experience quantum uncertainty, too small to feel the cosmic forces that shape galaxies. Yet here we are, conscious, aware, capable of measuring both the Planck length and the diameter of UY Scuti, capable of understanding nuclear fusion and gravitational collapse, capable of looking up at the night sky and knowing, truly knowing, that those points of light are distant suns, some larger than our imagination can hold, separated from us by distances so vast that their light is ancient history by the time it reaches our eyes. The universe is not required to make sense to us. It is not required to be comprehensible, to fit within the limits of human intuition. And yet, through patience, through mathematics, through centuries of careful observation and thought, we have begun to map it, to understand it, to hold it in some small way in our minds. The observable universe extends 46 billion light years in all directions. Beyond that boundary, light from more distant regions hasn't had time to reach us yet. And beyond that, we don't know. The universe may be infinite, extending forever in all directions, filled with galaxies and stars and planets beyond counting. Or it may curve back on itself in ways our three-dimensional minds struggle to visualize. We simply don't know. What we do know is that in this vast cosmos, on one small planet orbiting an average star in an ordinary galaxy, matter organized itself into configurations complex enough to wonder about its own existence. Life arose, consciousness emerged, and now, a few billion years after the first stars formed, here you are, reading these words, contemplating the scale of everything. You are small, that much is true. Smaller than Earth, which is smaller than Jupiter, which is smaller than the Sun, which is smaller than Sirius, which is smaller than the hypergiants, which are smaller than the galaxy, which is smaller than the observable universe. But you are also made of atoms that have witnessed the entire history of the cosmos. You carry within you the legacy of countless stellar generations. You are a way for the universe to know itself. And in that knowing, in that awareness, you are profound. You are part of this, not separated from the cosmos, but woven into it, made of it, one with it. The universe is vast beyond measure, and you, impossibly small, are here to witness it. that is enough. That has always been enough. Rest in the cosmic scale of all that is, all that was, and all that ever will be. And know that your brief moment of consciousness, your tiny flicker of awareness, is part of the grand sweep of cosmic time. A star burned for billions of years so that you could be here now, marveling at the magnitude of existence. And somewhere on an unimaginable scale, the universe dreams through you as you dream of the universe.